All right, everybody. Hey, don't feel shy. If you want, you can move up front. Yeah, you over there. Let's move up front. No. Anyways, it's 10,000 yen into the sea. This flipper. Let's give him a big hand and say something like, "Woo! Come on! Awesome."
Hello. So, as he said, I'm Flipper. This is my talk, 10,000 yen into the sea. Essentially, well, I mean, just to start with, can I get a show of hands? Who enjoys filling up their gas tank? Yeah, I'm not a big fan of it either. Actually, I spent 4 years commuting to and from my community college. 4 years, 2-year program. I had other things to do. So it was a 45-minute drive each way, so I pretty much ended up putting about as much money into my tank as I saved by living in my parents' basement. So all the benefits of living in my parents' basement with none of the cost savings. So that was kind of an interesting experience. And the reason why this is relevant is shortly after college, I saw underwater gliders, and they kind of blew me away because when you see the typical range and duration of these things' missions, it's pretty incredible. Around 3,000 kilometers on a single battery pack charge. And I work with electric vehicles professionally, partially as a consequence of this project. And I got to say, if you can show me a Nissan Leaf that can go 3,000 kilometers, I'll be pretty impressed. One of my coworkers says it's all about the drive cycle. So, as I said, I'm Flipper, and this is kind of what I do, electric vehicles. Professionally, they're ground vehicles here, underwater. I keep on trying to talk my boss into letting me turn one of our vehicles into a submarine, but so far, no such luck. So, you know, I'm finished with my education and not much in the way of job options at the time, kind of dead-end jobs, and I'm killing time in the bathroom because I didn't really like my job. Reading the Oregonian, and I see an article on Oregon State University's underwater glider program. And, you know, they were talking about how they work. They show a little cutaway diagram, and I'm kind of blown away. It's all like, wait. Like, how much do these cost? I could do that. You know, $100 tops. So that's where the 10,000 yen comes from, is at one point in history, that was about $100. A little bit of Jules Verne's too. So in order to build an underwater glider for $100, you kind of have to be an engineer, you know, or hacker, one of the two. I definitely wasn't an engineer, so I guess that's why I'm here at Defcon with you guys. You know, how do you design an underwater glider? You have to learn how to design an underwater glider. So it was really the start of an education, you know, self-taught in design and manufacture of underwater vehicles. So was studying machine tool technology at the time, manufacturing engineering type stuff, eventually got a transfer degree. And so yeah, it was a great vehicle to actually learn, and it gave a really good incentive to, you know, study STEM subject matter, and ultimately transitioned into an interest in an engineering transfer degree. So what is an underwater glider? Normal underwater vehicles propel themselves through the water using a propeller. Pretty straightforward. There's no propeller on an underwater glider, generally speaking. They use something similar to a fish's swim bladder to change buoyancy in the water, and as they float to the surface, they have wings on them. Does this thing work? Apparently not. So, wings, and those actually help transfer the change in altitude into forward movement. And so the efficiency of the vehicle is going to be determined by a couple things. First of all, the efficiency of your fish bladder buoyancy engine. Your drag, big factor is your drag. And then also kind of related to drag is your glide ratio. How many feet forward you move through the water for every foot you lose or gain in altitude. One interesting thing of underwater vehicles is they spend about half the time flying upside down because, you know, your gravity vector flips its head when you are going against the water column or going down with it. So, yeah, they're autonomous underwater vehicles that can travel long distances on battery power. So history, it all started back in, 80s or something. I wasn't even born yet, so it doesn't really matter. Very egocentric view of the universe. So they had these things called Argos floats, and they were essentially, a coffee can with a big linear motor powered syringe, and they'd go down through the water column and they'd collect sensor data. And then when they had enough data, they'd float back to the surface, satellite modem, phone home, and then they'd do it all over again. And based on my understanding of how things went down, one person was like, well, these things are really cool. We're getting really good data. We're not having to send people out in boats at, $40,000 a day. But the problem is we can't actually control where they go. They're kind of like hot air balloons. So it was like, what if we strap wings on them? And underwater gliders were born. Henry Stommel was one of the people who wrote some kind of pioneering articles on the potential applications of these things. And what you see before you today, between the Scarlet Knight, the Slocum, the Spray, it's become a very popular vehicle class simply because of the range you can cover for the amount of energy you have to store. So the Scarlet Knight is one of the record holders. It was put together by Rutgers University, and it was essentially a Slocum glider that had been, loaded down with extra battery mass and stretched out a little bit. Uses lithium CSC cells, is my understanding, which is kind of impressive because the high test peroxide rocket fuel you see in the movie Moonraker, as far as I can tell, actually has lower energy density. So those are pretty impressive batteries, although also fairly expensive. That's not what I ended up using. So I don't know if this is the correct way to design an underwater glider, but after going through 10, 20 designs in my head before even trying to build the first draft, this is kind of what I settled on as the proper procedure. Maybe somebody can correct me if I'm wrong, but you don't really know how you can package your components until you know what your components are, and buoyancy engine being one of the key elements that's going to determine the efficiency. You really have to start with that. Energy storage system is going to be dictated by the energy requirements of your buoyancy, and then whole design. It's a pretty straightforward process, very few moving parts. So eventually I did, I'm not a very decisive person, but eventually I did, come to a conclusion on how I wanted to build one of these things, and that was with a phase change material. There's another vehicle out there that uses PCMs to propel itself through the water. It's called the Slocum Thermal, and I'm not doing that because it looked really expensive. I read some NASA tech briefs kind of talking about that concept, and I think it was like N-pentadecane was the alkane they used, and really expensive per ounce. Wasn't really on the table because my goal going into this was, remember, I said I could do this for $100. If I'm spending, $200 on my my phase change material, I'm kind of already blown out. So these were the design requirements I went into it with. I wanted the barriers to entry to be super low because even though I had access to a milling machine and a lathe, not everybody does. So I wanted all of you to be able to take your Defcon CD, take the solid models that are on there, and go home and build one of these yourself. And then, range of efficiency, you're not going to take a 2 order of magnitude reduction in cost without, taking some hits on range, efficiency, performance. So it was kind of a best effort basis. I'm pretty optimistic. I've got a fairly large battery pack compared to the currency, or compared to the current consumption I'm looking at. So we'll see. Here's one of the earlier efforts I made into actually trying to design for manufacture. That's a Harbor Freight air compressor gear being used to index several syringes. And this design actually served as a little bit of inspiration for a hack I had to make towards the end of this project. Overall, the check valves involved were kind of a prohibitive feature that just disillusioned me of this concept. So considered a lot of things. I struck out electric motors, linear actuators pretty early on in the process because, at the time, lathe and milling machine were pretty much, a requirement to make those happen. The weight of using an off-the-shelf linear actuator was pretty massive. You'd end up with like a scuba tank pressure housing, and that's no fun. So wave and solar power, interesting concepts. I'd like to explore them a little bit, especially for one concept I might mention at the end. But overall, hydraulic pumps and phase change materials kind of showed out to me as the best choices available. So paraffin wax expands 10% when it melts-ish, and it's got a very high specific heat. So when it does melt, it'll stay liquid for a very long time. So I was looking at using soldering irons as a resistive load to actually melt the wax. And this is just a kind of a breakdown comparison of various energy densities I was looking at for kind of guiding my decision on how to build the buoyancy engine. And when I first started on this project, there really wasn't much in the way available of low-cost inertial navigation. You had the multi-Wii project, which I thought was pretty genius. They took a nunchuck and a Motion Plus from a Wii game console, and they actually made a 6 degree of freedom IMU out of it. Welcome to the future. This is really cool. This is a $33 board available from Hobby King, and I can't imagine they have more than $5 of profit margin built into that. You get a really cutting edge chip on there called the MPU 6050 or 6000, one of the two, depending on if it's SPI or I2C. But the point is, it's got a built-in magnetometer, and so it can do complete 9 degree of freedom sensor fusion, which is the ability to distinguish between gravity and linear movement through space. And when you're trying to actually integrate your inertial data, you'll run into problems unless you have some pretty good math background or a fantastic product like this behind you. That's the 3DR Robotics GPS chip. It was available, and it's actually buried in the nose cone of my vehicle right now, coated in a nice thick goop of RTV compound. Whole design was kind of fun. I spent most of the past year working on that at a specific aspect because it ultimately guided the production of the rest of the vehicle. Once I knew what I was packaging, I had to actually wrap it up into some sort of fluid dynamic hull form. And so based on the research I'd heard some interesting things about 30-to-1 glide ratios with something called a McMaster's airfoil, which was pretty much a NACA 4-digit series 0030. But based on the simulations I did using a program called Profili 2, marketed at RC Plane Design, its main claim to fame was it didn't stall out at high angles of attack, whereas the black line has one of the sharpest peaks on there. So NACA 009 or 0009 was kind of out of the question too. So kind of middle of the road choice of the symmetric airfoils that were well understood at the time. Pretty common options are NACA 0015-ish. So I think my wing root is NACA 0015 and wing tip is NACA 002. And what that does is hopefully like the Rutan Long Easy, if you end up stalling out, the wing root stalls before the wing tips, and that will cause the pitch to self-correct. Fingers crossed on that. Not a lot of testing in that regard. So first concept, I took a polycarbonate tube, a wax motor used to control a dishwasher latch, funny enough, high force, high latency, low efficiency, unfortunately, as I found out later. And oh no, I'm not sure if I'd submitted my CFP at this point, but I was kind of sweating at that time because I'm apparently really, really bad at fiberglass. Who knew? The original idea was that I would be using hot wire foam cutting techniques to actually generate the hull form and then lay fiberglass over it. And as you can see from this picture, that wasn't going so hot. So not as easy as it looked on YouTube. Was not going to hit my deadline at that rate. So throw money at the problem. I've generally found that when time is of the essence, money can generally buy you time back. So I bought a 3D printer. I really am happy I made that decision. 3D printers are really cool. One of the design requirements, being able to build this thing in my underwear, check. So similar design, same hull form, but now broken into smaller chunks to help with the print volume, and also trying to minimize the overhang of the printed parts. Support material is an option, and one of the largest prints on there actually was using support material. But 1 month turnaround time, you really can't argue with that. And I knew 3D printing could really help expedite the design process and getting you through multiple iterations. But until I'd experienced it firsthand, kind of saving my bacon on getting a proof of concept out the door and second, third revision, whatever, I was incredibly impressed with the value. That 3D printer I showed was a Rostock Max. It's a Delta Bot style design, and they are one of the coolest to look at when they're running. Cartesian Bot's a little bit lame, in my opinion. And that's the robot you see in front of you. So, $100 price target, $31 a kilogram for my plastic. That could be cheaper, but let's try and be generous just to make sure I don't underestimate. So $21 in plastic. So if you throw a significant amount of capital investment at the prospect of building injection molding tooling, then that could come down significantly. Remaining bill of material was actually published to the DVD, if I remember correctly. And I mentioned there may have been some hiccups along the road. This bill of material is definitely not accurate to the 30-cent mark, because the phase change material concept ended up working out to not just moderately inefficient to virtually unworkable, at least with the energy storage system I selected. If you need your robot to go to the bottom of the Marianas Trench, the fact that it's a solid to liquid phase change as opposed to expansion and contraction of a gas really working to your advantage. But if you're going for range and you don't particularly want to be dragging bottom with seaweed, trying to get 3,000 meters of depth with that process, probably not the most efficient use of battery storage. So I think it was early May when I realized, wow, I've got a 200 volt pack or whatever, and it's browning out at 100 milliamps, 0.1 amps. I knew that coin cells weren't exactly like lithium polymer RC plane batteries, but I was a little bit blown away. So I needed a plan B, or plan C, I guess. So what I came up with was something a little bit more conventional, trying to avoid too many experimental, wild concepts in one vehicle build can be a lifesaver. So I went to the tried and true electric motor linear actuator, because if you remember, at the time, my perception was those weren't really an option because people wouldn't have access to a lathe and mill. But with a 3D printer, that potentially changes. So I ended up using commercial off-the-shelf McMaster car parts to build the assembly, which you can see in white on the actual robot now. So the only change between what's on your DVD and what actually is here in front of you is the white assembly. Everything else I was able to recycle between designs. So modular design is a good thing, I guess. The gray pipe was a really good choice. Sorry about that. The gray pipe was a really good choice because it allowed for routing of the wiring, and ultimately acted as kind of a skeleton or a backbone for the entire vehicle. What I learned from that process is 3D printing is awesome, and the great thing is when you're actually done with it, you don't have to go through an entire twisted new process to design 3D printed or injection molded parts. You're practically already there when you have a working prototype. What did I learn through the process? I feel like I actually hit a pretty good balance between fail early, fail often, and not making stupid mistakes for lack of planning. I didn't build anything before I had complete solid model data. And that's really valuable when you're trying to avoid, these last minute crazed runs to Home Depot, West Marine, AutoZone, whatever it is. If you have a complete bill of materials before you make the first part, you know exactly what's going into the thing, and you don't find yourself running into these issues where parts are colliding with each other. And then it was also extremely difficult to quantify whether or not a design decision was a good or a bad one, such as the wax motor, until actually trying it. So it was a design decision trade-off to not use so much simulation. And I was pretty happy with how that went, because you can simulate the daylights out of a bad idea and then find out, you wasted the last year doing, FEA or CFD on a broken design, and then it's all wasted. So prototypes can illuminate things that you otherwise wouldn't be aware of. So I did this entire thing out of pocket, no grants or funding agencies, and I actually really like that, because I'm accountable to myself, and I don't have anybody breathing down my neck forcing me to chase sunk costs or make bad decisions because, I need to save face over that $1,000 I wasted on wax motors. On the other hand, I gave pretty much the profit of the design away for free on the DVD this year. I've probably spent around $15,000 on the project over the past decade. And so I would consider it a dubious appropriation of my retirement savings. But, that was the mission from the start. I wanted people to be able to build these themselves and kind of empower themselves to deliver sensors, communications devices, and payloads to remote destinations where traditionally it would be prohibitively expensive at tens of thousands of dollars per vehicle. And how that's possible is if your price is low enough, you can consider it disposable, and you don't have to pay somebody $40,000 to go out in the water and change the batteries. So we'll see. Ultimately, if you build it, they will come. And if it's a good idea, hopefully people will say, hey, maybe we should build some of these. So where to go from here? I didn't have an opportunity to test max depth because I only had one prototype as of 2 weeks ago. And I didn't really want to lose it out in the ocean scuba diving. Like, I guess I could have tried to put a dog collar on it and, walked it with a leash. But overall, it's disposable after my talk is over. But thing took over, 100 hours to print. And actually, that guy right there put in a significant amount of labor helping getting this thing ready for your guys' eyes. So small applause for him if you're willing. Thanks, guys. In terms of trimming vehicle, I can say with high degree of certainty this thing is very positively buoyant. Traditional buoyancy foam, polyurethane or epoxy, and glass microballoons. High crush depth, kind of unnecessary seeing as how I designed the vehicle with syringes, but overall a good choice. So generally speaking, epoxy or urethane, I chose paraffin wax. It's low cost and over half the dollar per pound of buoyancy I was seeing was either epoxy or polyurethane. So paraffin wax is like $4 a pound. So very positively buoyant. Every empty cavity in that entire thing has a specific gravity about 0.5. So it's really just a matter of how you distribute your lead and batteries at this point to make sure that when the buoyancy engine's in a neutral position, it's sitting about horizontal. Because when the vehicle goes buoyant, the center of buoyancy moves forward on the vehicle and it pitches towards the surface, and the GPS chip starts rising up to the daylight. And when it goes negatively buoyant, the opposite happens. So if you're in neutral buoyancy, you should be sitting around level in the water, and it's really just a matter of adding weight and removing buoyancy foam as necessary to achieve that. I'm looking at around 40 to 50 milliliters of displacement change. So it's unknown at this time what the vehicle's velocity through the water is. The more buoyant it is, the faster it's going to pop to the surface like a cork. And your speed through the water is going to determine what the Reynolds number is, and that guides things like what airfoil you select. But first draft, I'd call it an alpha stage design, and openglider.com is where I'm going to be adding future revisions. The one on your CD is Rev 0.1, and Rev 0.2 will be on openglider.com tonight, and that will have the new white syringe-based assembly. So yeah. In terms of research that went into this, this guy named Bruce Carmichael was one of the pioneers of the airfoil you see before you. It's called the X-35, and originally it was known as the Dolphin. But if I understand correctly, they ran the Dolphin through a genetic algorithm, and ultimately the citation shaping of axiometric bodies for minimum drag. That one, I think, was where I was able to find the coordinates for this design. It does bear some resemblance to some other vehicles on the market, and that shouldn't be too surprising, seeing as far as I can tell, we did use the same curve rotate around its axis to generate the main body. Otherwise, the NACA 4-digit series, pretty common equation. And I threw something in here that I found really fascinating. It's the geometry of a blended wing body morphing wing. And that was the idea that you could actually design an entire vehicle around variables and equations. So you can change something like a static wing sweep from 30 degrees to 15 to 25 degrees. And rather than having a lot of hard engineering labor going into remaking the entire design, it just regenerates itself. So very early on in the process, I was trying to stick to that concept, and I was pretty pleased. I would change a variable from like NACA 4-digit, 002 to NACA 005, kind of crazy. And, hit rebuild, and the model would, regenerate itself with very little labor on my part. One thing I'd like to explore is potentially even doing a genetic algorithm around that concept to optimize for parameters like speed through the water column and lift to drag ratio. So that's pretty much how I got here. The X-35 took me like 6 months to a year to even find. I had no idea where people were getting this curve from, but I saw it in several places. Ultimately, it was just a mad Google foo that was able to illuminate the coordinates to build this thing. And in terms of other information on how to build an underwater vehicle, I was going to joke, every story's hero has a favorite weapon. Brock Sampson's Bowie knife, Will Smith's little cricket, and Flipper's hot glue gun. When you're trying to waterproof stuff, I've tried a lot of different things: conformal coat, epoxy potting, pressure housings, and overall, even paraffin wax. Actually, it's not going to do very good in the Caribbean where the water gets damn near 80 degrees Celsius. And so, but it does a pretty good job, because when you pot your electronics in epoxy, it's very difficult to actually recover them or repair them if something blows up. But when you're using paraffin wax, the 80 degrees C melting temperature is actually below the rated temperature for most electronics. So if you decide you want to change something about them, and I've had to, you can just use a hot air gun or boiling water to rescue your electronics. That said, from a durability standpoint, paraffin wax, even if you anneal it with a little bit of mineral oil, not the most durable thing ever. So ultimately, hot glue has been my favorite approach to waterproofing. And if you need something a little bit lower viscosity, get down in the English muffin nooks and crannies, then they make low viscosity silicone RTV. The acetic acid can potentially corrode your electrical contacts, but we're talking about disposable vehicles here. It doesn't have to last 3 years. I've got electronic speed controllers I potted for the RoboSpub competition 2 years ago that still work, and that was just plain Jane AutoZone RTV compound. And so pretty much every piece of electronics on that thing are just either coated in hot glue or RTV compound, and it's a pretty easy, low-cost way of waterproofing electronics. So I guess at this time would be a good way to go for questions.
Can you control it by any chance? Like, can you remotely? And is there any way you can prevent it, like hitting something?
Yeah, that's a good question. So one of the problems with underwater vehicles that makes them kind of interesting to me is unlike Mars rovers, easy environment, aerial vehicles, a bunch of lightweights. These people, they're so spoiled. With underwater vehicles, you don't get to talk to your robot after you let it go. until it comes back to the surface, at which point, it's kind of a surface vehicle until it goes back underwater, snorkel depth style. So no radio frequency communication, so it has to be pretty much all autonomous. And the source code I used with the IMU to actually, it's called a Haversine formula. It finds your current GPS coordinates and your destination GPS coordinates and gives you a bearing and the distance you need to go to get there. So it's pretty much a line follower robot. That's what makes underwater gliders potentially so successful, is unlike, mine detecting robots or, anti-frogmen stuff. They have a pretty basic mission, which is go from point A to point B. So object avoidance potentially with sonar, but suddenly when your payload starts getting into the high dollar sonar stuff, it stops being so disposable. And at that point, my 3D printed open glider may not be the best choice of vehicles. So testing has been kind of an iterative process. I've learned every time I stuck it in the bathtub. Early on, it was pretty much with a small car battery and some red and green wire hanging out of the thing. Underwater vehicles can actually be communicated with remotely using something called a tether, at which point they're no longer AUVs or UUVs, they're ROVs, remotely operated vehicles. And I had 2 years of tethered vehicle competitions that kind of prepared me for working with the unmanned side of things. And it's a pretty good way to go. So for testing, bathtubs are surprisingly effective. You have them in hotel rooms. Generally speaking, the main thing you're going to be testing is either what it decides to do when it gets in the water, or how it sits in the water when you put it in there. And both of those things don't require a big swimming pool. Also, a lot less terrified, shrieking swimmers running away from the evil robot. It's the second one. So I don't really rely on pressure housings as a rule. I had to depend on some amount of air cavity for the design fix. And it's the most conventional thing about this design was you've got little linear actuators driven by 3-volt gear motors. Actually, I think I have one. Anybody want one? I know audiences love things being thrown at them. Not you, Mark. Hey, speaking of that, anybody want a flight controller? $33 give me? Remember, 2 is 1, 1 is none, so bring spare parts. Oop. Sorry. I throw like a roboticist. More questions? Oh, good question. So when you have like a tank light when you're scuba diving, you can actually make them water activated, so they are only wasting battery life when you're in the water and you're trying not to lose your dive buddy. In my case, I don't have anything smart like that on my robot, so those wires allow me to disconnect the power supply from the actual microcontroller, because once I plug it in, it just goes and it'll keep going until I unplug it. Ooh, really good question. I was at an ROV conference, and this guy who was like super salty, had been out in the field for a long time, told me a really cool trick. You go to like Harbor Freight, and they'll sell these heat shrink packages, marine heat shrink, and it's just heat shrink that's been lined with hot glue. And you don't need to use special heat shrink or wire crimps. You can just take your wire splice, coat it in hot glue, and then run heat shrink over it. And when you melt the heat shrink, or shrink the heat shrink, it'll melt the hot glue again and pull all the air bubbles out. Great question. How does it what? Oh, yeah, no, I totally glossed over on that. Really good point. So I don't actually have one buoyancy engine, I have 4. And generally speaking, you might have them towards the top of the vehicle. I have them low on the center of gravity because I had 2 places I could put them, top or bottom, and the top was all being used by syntactic foam or syntactic wax, buoyancy sand. Since that was more buoyant than the buoyancy engines themselves, I have them down low. And so I have broken the cross section of my vehicle into 8 little slices of pie. The top 4 are full of buoyancy sand, and the bottom 4, there are 2 pairs. So when you trigger the 2 on the left, your left side is going to be more buoyant than your right side, so one wing will lift up. Likewise, if you use the 2 on the right, it's going to change the attitude the other way. So this is one unique thing about my vehicle design. Traditionally, you actually move your battery mass, whereas I'm just having 4 times the buoyancy engines that are typical. And finally, if you change buoyancy on the bottom 2, then you'll just go straight.
Assume you have to use your inertial system for just minute-to-minute operations. How often do you have to go to the surface to get a GPS fix to how accurate is the inertial?
Oh, good question. So I can say with pretty good confidence that my inertial navigation system is not, high enough quality to be U.S. munitions list grade. So that's totally a relief. Yeah, these are hobby components. So video game grade. In terms of actual integration of my velocity or whatever to get my position, I don't really do any of that. I've been working a little bit in my free time with trying to use fetal Doppler monitors, which measure the velocity of fluid through a baby's blood to let you listen to the kid's heartbeat. Kind of cool. And they're essentially homodynes, ultrasonic homodynes. And I've been looking at potentially getting some velocity information from that. But pretty much I figure out which direction I want to go. And it's a line follower bot. It says, I know I need to go either left, right, or straight. And it dives and it comes to the surface and it says, oh, wow, I missed my target, but okay, now I need to go. It doesn't really look backwards, only forwards. Good question. Thanks.
How deep have you tested it to?
Ooh, bathtub depth? Okay, originally I had a washing machine wax motor from I think it was a Whirlpool Neptune or something. And that one didn't get a lot of mileage simply because the fiberglass thing went so terrible. It just didn't really work into the 3D printed picture. So then I moved to a soldering iron based design. I was using silicone, high temperature rubber hose and soldering irons and filling them with wax. And I was browning out my power supply. Even though I only needed about 100 milliamps, it was still too much, and it would have been a pretty big design tear-up to change my batteries, so I just changed my buoyancy engine. Questions?
What about sensor packages? How much room is there for any kind of reading system? Is it all
Really good question. So in the original solid model I designed around, I actually made a solid model of the PX4 autopilot from DIY Drones, or PX. I don't really know what that relationship is, but it's a really good board. It uses a publisher subscriber system, and so right now I'm only using the IMU, the MicroWii board, for everything. And one of the issues with that decision is it is so flash memory constrained that you can only just barely compile the source code and include it on your DVD. In fact, if you try and use Arduino 1.5.2 to do so, it's not going to work for you. You have to use Arduino 1.0.4, if I remember correctly, and that will work. So didn't remember to put that into the slides, and I'm glad you brought it up. So there is a reasonable amount of space, about 1/4 the size of an Altoid 10, maybe half the size of an Altoid 10, for a supervisory controller to supplement the IMU. The IMU is broadcasting yaw, pitch, roll information that's already been fused, so it's pretty much relative to your world body or world coordinate system. And it's really nice because it's publishing it on the serial port, and it's also telling you. Oop, time's up. All right. Any further questions or wanting to see the robot in person, touch and feel? I'll meet you guys out in the hallway, I guess. Thank you.